Okay, our last topic on finite difference method is solution techniques. So, as I mentioned, the basic idea of the finite difference method is you develop an equation for the head at every node, which uses the way we formulate that equation is we reference the head at the adjacent cells, and we do it in such a way that the governing equation is satisfied. And we take into account all these special cases: anisotropy, no flow boundaries, specified flow boundaries, etc. And we end up with a big set of equations. We have one equation for each node. All right, so how do we go about solving those equations? We're going to talk about, there are actually quite a few more solution techniques that we'll show here, but we'll show some of the classic techniques for solving these equations. One of which is called relaxation. And so, for example, let's suppose we're looking at node I, and remember HI is equal to 1/4 of HL plus HB plus HR plus HA. But if you multiply both sides by 4 and then take everything to one side, you can write the same equation in this form where everything is equal to 0. What that means is if the heads at all 5 of these nodes have values that satisfy the governing equation, then when you add them up like this, the result will be 0. Okay? So what we do to start out is we don't know what the heads are, right? So the whole point of this is to find a set of heads that satisfy the governing equation, so they make this equation balance. So if we guess at a set of heads, and then using our assumed set of heads, we evaluate this equation, it's not going to be equal to 0 on the first try. It's going to be equal to some value, which we're going to call the residual error. And so our objective is to keep perturbing these head values until this equation is balanced and that residual goes to 0. So what we do then is we examine the residuals for all of the nodes, and then we find the node with the largest residual. And then at that node, we assign HI to using our governing equation. So we take the heads at the other nodes, which maybe they don't, 100% balance. But then we apply this equation and adjust HI. So now at node I, the governing equation is satisfied. Well, then using that head, we adjust we calculate the residuals at all of the other nodes, and then we find the node with the largest residual, and then adjust it again using this. So we basically repeat steps C and D over and over in a loop until eventually those residuals will get smaller and smaller, and they'll finally converge. It gets under once it reaches some tolerance, then you can stop. So this is it's a very simple algorithm. It may not be the most efficient algorithm in terms of time to solve, but it's a really simple thing to implement. Another method, which is really common, is called iteration. Well, relaxation is a form of iteration, but this is a little bit different. And so with iteration, we take our governing equation, and let's just assume the simplest case, 1/4 of HL plus HB plus HR plus HA. Have a similar kind of equation where we have boundary conditions. And then again, we start out by assuming heads at all the nodes where the head is unknown. And then we just sweep through the entire grid, and at each node, we readjust HI based on the heads at the other nodes using this equation. Okay? And then we just keep doing that over and over and over again. And Eventually, if you do that enough times, eventually the delta DH, DH is the change in head. This should have been delta H here. Eventually, you look at the maximum head change for a given iteration. And an iteration involves adjusting all of the nodes in the entire grid. That's a single iteration. You keep track of what the biggest head change is during that iteration, and you continue iterating until the largest head change is smaller than some tolerance. Now, when we use Excel, when we set up our finite difference equations in a spreadsheet with the circular references, and we turn on iteration as a solution option, we tell Excel how many iterations we want it to do. And, we go until those head changes are really small. And so this is basically what we do in Excel when we solve it. But you can also, this is very easy to code if you're doing it in a programming language. Very simple solution technique. All right, the other technique we'll talk about is called the matrix method. And to illustrate how this works, we're going to show, we're going to derive the equations for this particular case. So if we have water flowing through this channel and we have 8 nodes, and we have a boundary condition on the left, h equals 100, and on the right, h equals 0, then that means we know the heads for cells 1, 2, 7, and 8, and we need to solve for the head at cells 4, 6, 3, and 5. In each of these cases, this is, we use our equation we derived for a node on a no-flow boundary with 2 pervious quadrants next to it. And so in this case, the head at node 3 would be 1/2 of the head at node 1, 1/2 of the head at node 5, all of the head at node 4 divided by 2. And a similar equation for each of these other cells. So we're going to have 4 equations here. For node 3, again, actually we're using, these equations are derived here using this residual form where everything is on the left. So we get 1/2 of H1 plus 1/2 of H5 plus H4 minus 2H3. Okay, so we're using H3 is the node that we're looking at here, and we just pulled it over to the left side, and we do that because we want to solve it to where all of the head values are on the left side. Now remember, H1 is 100, and so if we have H1 divided by 2, that's 50. So we move that over to this side, we get minus 50. And then we also order these head values to be in terms of their suffix. So we move H2H minus 2H3 here, H4 here, and then 1/2 H5 right here. And we get this. This is the form of the equation we want to use for that node. And likewise, we do a similar thing for node 4. H3 minus 2H4 plus 1/2 H6 equals minus 50. We're skipping this intermediate step here. And then for node 5, we get 1/2 H3 minus 2H5 plus H6 equals 0. And node 6, 1/2 H4 plus H5 minus 2H6 equals 0. So in each of these cases, we have all of the heads on the left. They're ordered in terms of their number, the suffix, the node ordering, and we have our constant values on the right. The reason we do that is we can then plug them into a matrix form. So we have our vector here is H3, H4, H5, H6. These are the, again, we don't have 1, 2, 7, and 8 because we know their values, and these become constants. So their values are what help us derive these boundary conditions, these constants on the right. So basically here we would say, if we have negative 2 times H3 plus H1 times H4 plus 1/2 times H5 equals minus 50. So that is this equation right here. And our next equation is H3, 1 times H3 minus 2 times H4 plus 0 times H5 plus 1/2 times H6 equals minus 50. That's this equation. And so forth. Each of these equations is now represented in a matrix form, which can be written as A times H equals B, where A is these numbers over here are purely simple coefficients, and these are the heads we're solving for, and on the right we have a vector of constants. So now we can simply apply a classic matrix solver to solve for the heads, and there are a large number of algorithms out there for solving a matrix like this. You notice that if we have 4 unknowns, this matrix is 4 by 4, so it's always n by n, where n is the number of unknown head values, or nodes with unknown head values. And these are always one-dimensional vectors, the size of the number of unknown heads. Another thing to notice is this matrix is symmetric and banded. So if you look down this axis, we have negative 2's here, but that may not always be the case. But look, actually, I think it is. If you look opposite around this band, so this number is equal to that, this number is equal to that, this is equal to that, this one's equal to that, and so forth. So the top half of this, if you just flip it, it's equal to the bottom half. If you've ever studied linear algebra, you know that this is what we call a symmetric matrix. It's symmetric around this diagonal. It's also banded. Now, this is just a small version, but what that means is once you get out a certain distance away from the diagonal, everything is zeros. Now, we only have one row out here at 0, but if we had, let's say we had a 50 by 50 matrix, then that band in the middle may be, I don't know, 4, 5, 6 elements wide, and everything else is zeros. And so again, it looks like this. We have a non-zero region, which is symmetric, and we have these zeros out here. Now, in cases like this, you only need to store 1/2 of the band. So there's no point in storing all these zeros up here or down here, and there's no point in double storing each of these. So you only have to store half of this non-zero region. And then there are canned algorithms you can use to solve a banded symmetric matrix. And so that really significantly cuts down on the storage we need to use, and also the time to solve it. And so anyway, there's no iteration involved typically in a matrix. Well, you can solve the matrix iteratively. I should be careful. That is one of the ways you solve it. But there are also direct solution techniques that just use an algebraic method to solve this. So that's kind of a summary of the most common solution techniques for the finite difference equations.